Now that we can draw chairs in different conformations, we can see the effects of having substituent groups and what kind of strain is involved. And you can see a Newman projection of butane. We have this gauche interaction where these methyl groups are kind of off kilter of each other. When you have it in a cyclohexane ring, these can interfere with each other as well and have different strain. So this table here shows us the 1,3 diaxial strain. So if I have a group where Y is listed, that can have steric interactions with the hydrogen that is in the carbon, that's on the carbon 2 carbons over. So our tert-butyl group right here, there's a lot of diaxial strain, so it's a very good chance that that tert-butyl group is going to whack into the hydrogen, which it really doesn't want. If you have fluorine, there's less of an effect because it's very small, but with the large groups, they really want to be in the equatorial position. So for cis 1,2-dimethyl cyclohexane, the interactions with the two methyl groups are not very large because this methyl group here that's in blue, this is axial up. This one is equatorial up. So the cis comes from them both being up. So if we were to draw this as a flat cyclohexane, we would have cis 1,2 where they're both pointing up, and that's how we would translate it into the chair. So this one has the axial up, equatorial up, and they're not very likely to run into each other. And then if we do a ring flip where this methyl group that was in blue and in the axial position gets flipped, that's going to go into the equatorial position. And our strain is going to be the same. These CH3 groups don't really interact with each other very easily. If you have the choice of either of the groups, in this case it's going to be pretty similar energies because they have the same groups. So in the trans 1,2-dimethyl cyclohexane, your structure might look like this. One is up, one is down. These CH3 groups here are both in the equatorial position because they're out and at an angle. And we can see those groups right here. So that's one. The other CH3 is right here. And they don't really interact with each other very much. But if we do the ring flip, my equatorial methyl groups become axial. And now all of a sudden, when this CH3 is rotating around, it could whack into either of these hydrogens, and the CH3 below can also whack into the hydrogens. So you can see that they're going to get into each other's space bubbles, which they don't really like. So this is the more stable version, or the preferred conformation. So some places that we might see these cyclohexanes in naturally occurring biological systems is glucose, and that's present in most sugar forms. In table sugar, it's a dimer, so there's 2 of the glucose units will form table sugar. We also see it in honey, and then we have mannose, which is another sugar. So the difference between these two, they are stereoisomers of each other, and they only differ in this one OH group, where in mannose, it's going to be in the up position, and in glucose, it's in the down position. All right, so our problem here is to draw the more stable conformation of cis 1-tert-butyl 4-chlorocyclohexane. So I'm going to start with the flat drawing first, and cis tells me that they're going to be on the same side. So I'm just going to draw them both wedged. At 1, I have a tert-butyl group. And at 4, I have a chloro group. And then when I go to draw my chair, my parallel lines here, and then if I number this here, 2, 3, 4, I'm going to start numbering here out of habit, but you can start your numbering wherever you like. Just make sure that your groups on your chair are consistent with the ones in the cyclohexane ring. So at 1, my group needs to be pointing up. The wedge equals up. And at 1, on my chair, the corner is pointing up. So that means that whatever is up is going to be axial. The tert-butyl group is going to be axial. And then at 4, I have a chloro group, and my corner tells me that whatever is pointing down is going to be axial, and my chlorine is up, so it's going to be equatorial. Right now, I have a large group in the axial position, which is not preferred. This one is not the most stable. So we want the largest group equatorial possible. Okay, so what I can do is just draw another chair. And I can just start my numbering one carbon over. So at 1, my tert butyl group is up. So that's going to be equatorial because the corner is pointing down. So that hydrogen is going to be axial. And then at 4, my up is chlorine. So I have 1 axial and 1 equatorial. The chlorine is axial. My tert butyl is equatorial, but I want the largest group in the equatorial position. That's the most stable one. So this is the most stable. So in the top structure that I drew, there's more likely of a chance of these tert butyl methyls whacking into one of the hydrogens that are axial up than it would be in the second structure. Okay, we have another problem here. We're going to draw trans 1,2-dichlorocyclohexane. So trans, we have one that's up, one that's down. So I'll start with my chair. And it says to explain why both chlorines must be axial or both equatorial. So if this is 1 and 2, 1 and 2. So if I draw my up corner here is going to be axial, so that's the chlorine. And the next one is down. So in this case, they're both axial. And if I did one, let's say where I shifted where number 1 was, this is going to be up, this one is down. These are both equatorial. All right, so the trans refers to the direction of the methyl groups. And the axial and equatorial, that just comes from the chair. So you can have it be trans, but both be axial, because the axial equatorial can always change when we do the ring flip. So in the first structure, I have them both being axial, but if I shifted them over 1 carbon, they both become equatorial. And it's always going to be that way because we have 1 chlorine up, 1 down. And in this first structure, we have a chlorine that's up, 1 that's down. This is still up and down. The trans in the cis does not refer to the axial and equatorial. So that's how we can have both chlorines be axial or both equatorial. Decalin is 2 fused cyclohexane rings. We can have a cis decalin and a trans decalin. So you can see how they're drawn there, but you will not be asked how to draw these, just for reference. The trans decalin is going to be the one that is preferred. This one is. And we can see that there's less angle strain here. It's better to have the small hydrogen be in the axial position than this one. So this one is lower energy. And then other places that we might see these fused polycyclic molecules are in testosterone, which is a steroid. We saw cortisone at the beginning of the chapter. We also have norbornane, which has a couple of bridged rings. There's a cyclohexane plus a ring, and then camphor also contains that cyclohexane ring. That one also has the bridge there.